Let's record. Okay, good morning, people. We are going to talk about little theropods today. So we were talking about big theropods last week, and as we refine our examination and we look at more and more derived clades leading to the derived birds that we know and love today, we find that the median size, which is the middle line in each of these bars, the median length of the animal gets a lot smaller as we go to modern birds. And there are many different groups of theropods that have small sizes. Another thing that we will be paying a lot of attention to this week is the way that the proportions of the limb lengths change in different theropod dinosaurs. Now remember, Microraptor did not turn into an Archaeopteryx, did not turn into a different kind of bird, but if we compare these things in a straight line, we can look at changes in the lengths of their limbs relative to each other. If we can compare a ceratosaur, let's look at the limb bones here. Let's look at the forelimb. We have the humerus, radius, and ulna, and then the hand. Humerus, radius, and ulna, and then the hand. This is a therizinosaur. It has 3 fingers, fitting that it is Avetheropoda, but also humerus, radius, and ulna, the hand. There's something else important on this animal, which is located at the wrist. It is the half-moon wrist bone that allows this arm to swivel more. If we look at the next one, we have a dromaeosaur here, and I can also highlight its arm bones for you. Humerus, radius, and ulna, and then the 3 fingers of the hand. Radius and ulna, and then the 3 fingers of the hand. And it's not shown very well in this picture, but this animal also has half-moon wrist bone. Consider these different clades of theropods. An important feature that pops up in Maniraptorans that we discussed last week is the half-moon wrist bone, which would be present in the last common ancestor of an oviraptor and a modern-day magpie and all of its descendants, unless they explicitly lose it somehow. This is the Sinosopteryx, which is an Avetheropoda, and it has the 3 fingers on the hand. Let's look at the proportions of this animal. Long legs, short arms, pretty big hands, and also this animal has feathers. Feathers on the neck, the rump, the tail. Simple filamentous feathers. If we can compare that to a very similar looking animal at first sight, we have long legs, longer arms, and some pretty prominent feathers on the rump and arms. This animal, Archaeopteryx, this is Maniraptora. This one does have the half-moon wrist bones. I'm going to go back in between those again. All right. The proportions of these animals are very similar. This animal is not necessarily flying. These feathers are not sufficient for flight, but it does have pretty big hands and it has those nice wrist bones. Similarly, if we look again at our therizinosaur, which has really big hands, it also has feathers that are not flight feathers. These are filamentous feathers that are maybe decorating or adorning its neck and tail and other parts of its body. If we consider Microraptor, this is a dinosaur we haven't discussed in this class yet, but it's pretty cool. One of the features that Microraptor has is feathers that are growing right off of its shins. Microraptor actually has effectively a wing on its long arm with a long hand. And Microraptor also has feathers growing directly out of the legs, which is one of the features that distinguishes Paraves from other Maniraptorans. But like other Maniraptorans, the Microraptor still shares the half-moon wrist bone. If we get into Archaeopteryx, this is now kind of familiar territory where we have a nice big wing, but Archaeopteryx still has feathers growing directly out of the shins. They don't necessarily have such a robust wing as Microraptor, but they did have feathers growing out of their shins, as with other Paraves, and they've got a pretty big hand, and they've still got the half-moon wrist bones that came from the Maniraptorans. Finally, if we look at Confuciusornis, I want you all to say, hey, look at that Paiga style. You are more or less a modern bird, dude. And look at the very large hands on Confuciusornis, which have feathers growing directly off of them that are flight supporting feathers forming a wing. And notice that Confuciusornis does not have the same level of feathers growing directly out of their shins. Their legs are more or less naked. And the naked leg condition is something that pops up in very derived theropods within Paraves. So even though Paraves is distinguished by having initially one of the traits that you can recognize them with is that they have feathers growing off of the shins, the more derived ones do not have feathers growing off of their shins. If we consider a Andean condor, here's the humerus, radius and ulna, and the finger bones. Notice how the finger bones are now such a big part of this forelimb. And that is one of the things that we see as we compare these animals, the forelimb getting relatively longer, and the radius and ulna doing a lot of that, the finger doing a lot of that as we derive birds. But remember, this is not a linear trajectory. Microraptor did not become Archaeopteryx, did not become a different kind of bird. Instead, we need to remember to place these things in a cladistic framework so that we can say, okay, well, the last common ancestor of Archaeopteryx and a modern bird had some features that distinguished them from their last common ancestor with Microraptor. This is what I want to impress you with this week. There are so many flying theropod dinosaurs with incredible feathered wings and all these different features to fly in different ways. It's basically a huge set of experiments, and a lot of them worked really well. If you went back in time and you looked around, you'd say, hey, look at all the birds. And they wouldn't all have the paiga style and some of the other features of our derived birds that are alive today, but there were just a ton of things flying and skittering around. Here are some pictures of them from a review paper where, we have varieties of things with just a little bit of feathers to a lot of feathers. This guy's dapping, I guess. And if we place that on a timeline, this is pretty radical. If we think in a linear fashion, okay, dinosaurs turned into Archaeopteryx, turned into birds, then you would expect those things that you would find big theropods early in the record and birds later in the record, and Archaeopteryx smack dab in the middle. But that is absolutely not what we see if we try to place these animals in time. Lots of large theropods continued to be expressed throughout this time, and this isn't even showing the giant Tyrannosaurus Rex, all that stuff. If we concentrate on this time tree, which shows us both their cladistic relationships and their placement through time, Archaeopteryx has been around for a really long time, since the late Jurassic. All right. And these small little theropod dinosaurs, including things that could fly, have been around for hundreds of millions of years. So small theropods are every bit as critical to daily life in the time of dinosaurs as are large theropods. They just don't get as much press. Finally, there's one feature that I want to look at, which is this hummingbird wing. Notice that on a hummingbird, the hand is enormous relative to the rest of the wing, and the arm bones are relatively short. That is compared to, say, a pigeon, hand bones, arm bones, right? Now, in terms of the hand bone being these fused fingers, as are found in other birds, and it getting larger and larger and larger in the context of directed flight, well, that makes a lot of sense, because that's something that is happening every time we derive a new clade. We are often getting bigger and bigger hand bones. And so you could call these big hand bones on a hummingbird an adaptation, because in the context of flight, those fused fingers getting bigger and bigger and bigger makes a lot of sense to have a wing that supports the animal's body weight. But there's this other feature that I've highlighted in pink here. When we consider the half-moon wrist bones, we have to go all the way back to Maniraptorans to think about the last common ancestor where the half-moon wrist bones arose. And these are animals that were definitely not flying, yet they had these half-moon wrist bones. So the context in which the half-moon wrist bone arose is not in the service of flight. And the context in which the half-moon wrist bone became inherited by all of these different theropods is not because it was good for flight. There is some feature that went along. There's some environmental context and ecological challenge set in which the half-moon wrist bone and the flexibility on these enormous, ridiculous hands conferred some success on these animals, or did not get in the way of their success, such that they are still have descendants alive today. But if we think about birds that fly with directed flight feathers, that half-moon wrist bone is pressed into service for the directed flight. And if we think about it in the context of hummingbirds, the only way that hummingbirds are able to hover is because their wrists are extraordinarily flexible. But the anatomy that allows them to take advantage of that flexibility did not arise in the context of flight. This is why we call it an exaptation, because the evolutionary pressures took a left turn. This wrist bone was handy for doing something with the hands on large theropod dinosaurs, and later it was co-opted into service for flight and even hovering flight in hummingbirds.